Swayam Prabha. Digital India. Educated India.
Hello everyone, so welcome to our last lecture on the tutorial session for Geology and Soil Mechanics. Now today we are going to continue the shear strength behavior of soils, and we are going to end at the shear strength behavior of soils. The list of the lectures that whatever Professor Priyankos will cover will be on the earth pressure theories and a few on bearing capacity, which I have already covered in the previous, which I have already covered a bit in the previous lectures, in the previous tutorial sessions. So we are discussing about a problem on an elastic soil and how to find out the Poisson's ratio for the problem on the elastic soil. So basically the problem stated that linearly elastic soil was present and you are supposed to find out the change in volume, that is delta V, when subjected to isotropic stress loading. Now we also said that the isotropic stress loading is basically in a p-cube space, and isotropic stress loading means the sample is not subjected to any shear stress. That means basically if the sample starts from a point at 0 0, then it will be at some point p dash 0 after an isotropic stress. Isotropic stress also means in realistic sense actually an equal confinement from all the three directions in case of a triaxial sample, which is generally termed as sigma 3, or you can also call that as sigma c. So an equal confining stress from all the three directions means it is an isotropic behavior. Now it is asked that what can you say about the Poisson's ratio of the soil. So we said that from the basic definition of mechanics, we said that epsilon can be written in the form of sigma by epsilon minus nu into, if this is epsilon x, then sigma x by y, sigma y plus sigma z by e. Now in case of a triaxial we also said that the two directions sigma y is equivalent to sigma z. So this equation turns back to sigma x by e minus 2 nu into sigma y by e. In a generalized term we can write this as epsilon I is equal to sigma I by e minus 2 nu sigma I by e. Now this can also be written as, so epsilon I is equal to sigma I by e into 1 minus 2 nu. The volume change, as we all know, is equivalent to 3 epsilon I. Now how did I get that? This is because the volumetric strain epsilon V is equivalent to the strain in x direction, the strain in y direction and the strain in z direction. Now from the problem itself it is given that actually it is an isotropic stress loading. That means basically it is subjected to equivalent stresses in all the three directions, which is sigma c and sigma c. So obviously if the elastic material is constant, means if E is constant in all the three directions, that is Ex equal to Ey equal to Ez, then epsilon will also be constant in all the three directions. That is epsilon x will be equivalent to epsilon y will be equivalent to epsilon z. So you can write this as 3 times of epsilon x, or you can write this as 3 times of epsilon I. So 3 times of sigma I by E into 1 minus 2 nu. So this is the total volume change. Now you have to consider, now this is the first question. The question for the first is answered, that is delta V. What is delta V equal to? So delta V you can write as 3 into sigma I minus E into 1 minus 2 nu into V, where V is the total volume of the soil sample. Now this is obviously volume of the soil sample before consolidation or before isotropic loading, before isotropic compression. So obviously this is only valid, remember this is only valid for a linearly elastic soil, but however it may be however you also know that a soil in a stress strain curve obviously has a elastic zone and a plastic zone. So, obviously, in this plastic zone these conditions are not valid. So, more higher terms will come in the plastic zone, which we will ignore because this is a basic soil mechanics course. So, only in the elastic zone whatever terms are whatever only in the elastic zone whatever the volume changes, this can be found out from this formula. Now, you have to consider, in order to find the Poisson's ratio, you have to first consider that the volume change is compressive in nature. So, if volume change is compressive in nature, that means delta B by V should be less than 0. That is one of the most important part, because in soil compression is positive, but when you consider a general, from the general mechanics, if you consider the definition of compression, or from general soil mechanics, from general mechanics, if you consider the tension and compression, the tension is always positive while compression is negative. Since we derived this formula from the basis of general laws of mechanics or general laws of solid mechanics, so in this case actually we consider that delta V by V should be less than 0 for compression. If this is true, then we can also write that 1 minus 2 nu should be less than 0. So, this implies that nu should 1 minus 2 nu should be greater than 0. So, delta V by V should be greater than 0 for compression, delta V by V should be greater than 0 for compression, because as I have said that in case of soils, if you consider the compression, then compression has to be positive in nature. So, delta V by V should be greater than 0. So, in that case 1 minus 2 nu should be greater than 0. So, this implies nu should be less than half, or nu should be equivalent to less than 0.5. Now, what happens if nu is equivalent to 0.5? Now, you all know that when nu is equivalent to 0.5, then this corresponds to delta V by V equivalent to 0. That means the soil is termed as incompressible. So, this is a general very easy problem on considering the linear elastic soil. Now, as I have said that you are given different, you are to perform different tests and you are given different parameters to find out. Let us say that from an odometric modulus you have to find out the odometric, from an odometric test, or basically from a consolidation test you have to find out the odometric modulus, even from a Traxel test you have to find out the value of E. So, the next question that I said is basically how you can find out the odometric modulus from this case. Now, it is said then in an odometric test, for delta sigma V increase in stress, a linear elastic behavior is observed. So, it is clearly given that the linear elastic behavior is also, that means all the definitions that we said in the previous part are all valid. Now, in this case you are asked to find out the relation between odometric modulus E dash, the Young's modulus E and nu. So, as I have said in the previous tutorial session that E dash can be also written as m, which is equivalent to 1 by mv. So, this means it is equal to 1 by AV into 1 plus E naught, which means it is equivalent to delta E delta sigma. So, delta sigma divided by delta E by 1 plus E naught. Now, if you remember the definition from consolidation correctly, then delta E by 1 plus E naught is nothing but equivalent to delta H by H. So, this is what is the definition of E dash. So, from here you can find out that delta sigma is equivalent to E dash into delta H by H. Now, this is also equivalent to delta V by V, since consolidation volume change is totally one dimensional. That is why in earlier lectures also I said that it is termed as Terzaghi's one dimensional theory of consolidation. So, delta V by V, as we said in the previous definitions, that delta V by V is nothing but actually equivalent to epsilon V. So, this is E dash into epsilon V. So, this is from the basic definition that we came, the definition of odometric modulus. Now, delta sigma is obviously nothing but just the increase in vertical stress, because you can apply odometric stress or consolidation test only in the vertical direction. So, if you consider that the odometric test in the vertical direction, then how can you find out the relation between odometric modulus, the Young's modulus and the Poisson's ratio. So, one thing you should remember that this delta sigma change is only for a small stress linear elastic behavior is assumed. That is obvious, because if you perform a stress strain test as well, triaxial, direct shear or odometric, you will see that this elastic range is very small. It may come within the 2% of the total strain, or it may come with, whereas the total strain may go up to as high as 20%. So, basically the 2% of the strain, or basically it is just a negligible portion compared to the total strain, and within that range only the elastic range is actually assumed. So, in this case delta sigma is also assumed to apply for that small range only, because it is said that the linear elastic behavior is there. Now, one thing you should also remember in case of an odometric test, that though it is never mentioned that sigma 2 is always sigma x is always equivalent to sigma y, that means sigma 2 is equivalent to sigma 3, because if you remember the odometric sample, or basically the consolidometer sample, this is how you apply the load sigma v. Now, it is confined in both the directions. Now, since it is confined in both the direction, it can extend or it can contract, or it can expand and contract only in the vertical directions only. So, this is where basically the delta v by v comes, which is equivalent to delta h by h, because if it expands in the horizontal, if it expands in the vertical direction, then there is a change in the reading delta h that is corresponds to, or that corresponds to the change in the volume of the sample, because it is confined in other directions. So, obviously the stresses in these two directions are actually constant, that means sigma x and sigma y are actually equivalent to one another. So, since they are equivalent to one another, so basically we can write that delta sigma is equal to E dash into epsilon v. Now, epsilon v is only in one direction. So, basically we can write that as epsilon 1 if we consider the vertical direction to be 1, the horizontal, these two directions as 2 and 3, that means our axes are like this 1, 2, 3. So, obviously sigma in this direction is the only thing that is changing the sample. So, epsilon dash into epsilon 1, or you can also write as delta sigma 1 is equal to E dash into epsilon 1. Now, you can also think that basically you can also come from this relation that epsilon 2 and epsilon 3 are actually confined by the metal rings, because you see that epsilon 2 and epsilon 3 cannot expand, only the stresses in these directions can expand, because if it is a linear elastic soil, then all the three stresses could be interrelated through the strains. So, epsilon 2 and epsilon 3 has no chance, or they are equivalent to 0, because of the only fact that it is confined with metal ring on both the sides, as you have seen in the odometric sample. So, obviously epsilon 2 will be equivalent to epsilon 3 will be equivalent to 0. So, I can write from the definition of epsilon 1 1 by E into delta sigma 1 minus nu into delta sigma 2 plus delta sigma 3, because the stresses in these directions are not 0, only the strains in this direction are 0. So, it comes out to be 1 by E into del sigma 1 minus 2 nu del sigma 3, because again I have said that sigma 2 is equivalent to sigma 3. So, that means del sigma 2 is equivalent to del sigma 3. So, if this is the case, then epsilon 2 is equal to epsilon 3 can be also written as 1 by E into delta sigma 3 minus nu into delta sigma 1 plus delta sigma 2, which is equivalent to 0, because as I have said previously that the strains in the sigma 2 and sigma epsilon 2 and 3 directions equivalent to 0, because sample is confined by metal rings on both the sides. So, delta sigma 3 must be equivalent to nu into delta sigma 1 plus delta sigma 2. So, from here we get that delta sigma 3 is equivalent to nu into delta sigma 1 plus delta sigma 3, because delta sigma 2 is equivalent to delta sigma 3. So, from here you can write delta sigma 3 is equal to delta sigma 1 nu by 1 minus nu. So, if you replace this in the equation of epsilon 1, you will get epsilon 1 is equal to delta sigma 1 by E into 1 minus 2 nu square by 1 minus nu. Now, remember we are deriving all this from the definition, basic definitions of solid mechanics, considering compression is positive, because we will always take, in case of soil, compression is positive. So, that is why I have ignored a minus sign here, because if you really want to observe, or if you really want to see that from the basic definition of solid mechanics how you can derive this, you will always see that there is a negative sign in front of this. There is a negative sign if basically you consider from the basic definitions of solid mechanics, where you take compression negative. But this all are from the definitions of solid mechanics, but we take the sign convention of soil mechanics. So, that is why epsilon 1 is always said to be positive. So, 1 minus 2 nu square by 1 minus nu. So, if this is the case, you all know that delta sigma 1 by E, or if you compare these two equations, then you know that epsilon dash now will be equivalent to, epsilon will be equal to epsilon dash into 1 minus 2 nu square by 1 minus nu, because epsilon is nothing but actually equivalent to sigma is equal to E into epsilon. Okay, so this E goes here, is equal to delta sigma 1 by epsilon 1 into 1 minus 2 nu square by 1 minus nu. From this it comes out, and delta sigma 1 by epsilon 1 you can easily see it is odometric modulus, because from the basic diagram of an odometer, or basically from the consolidometer, you can see that sigma 1 is the stress applied in the vertical direction, epsilon 1 is the volume change in that direction. So, obviously it is a one dimensional consolidation, and hence it is nothing but equivalent to the odometric modulus. So, that is why we can write this as E dash or M, whatever you want, and 1 minus 2 nu square by 1 minus nu. So, within an elastic range, or if you consider an elastic range, this is what should be the basic relation between Young's modulus, odometric modulus, and the Poisson's ratio. Now, for a particular Poisson's ratio, you can also find out the Young's modulus and odometric modulus from these relations. Now, one thing is that this is a bit high end problem, because these all require some basic things which are termed as the basic definitions of solid mechanics, and one of the things that it requires is the constitutive relations. So, this is just a demonstrative problem that how people generally model a soil mechanics from an experimental to a computer program. So, this is how they use the definitions of stress, strain, Young's modulus, and all those things to basically predict the behavior of soils at different stress levels and confinements. This is only considering linearly elastic range. Similarly, you can consider plastic range, and you can go for the plastic behaviors of soil, but this is an entirely different domain. This is only just to demonstrate that how basically the shear strength relations of soils can also be used for modeling behaviors. Now, coming back to our original basic shear strength relationships, we will now cover a very important problem regarding stress paths. Now, this stress paths problem is also a discussion problem and not actually a solving type of problem. So, here basically we will discuss that how in different types of tests the stress paths actually differ from for a particular material. So, it has been asked that the following tests are performed one of which is termed as the consolidation test. This can also be termed as an odometric test, because right now you know that an odometer is equivalent to a consolidometer. So, in this case they are asked to find out that how the stress paths actually look like in a PQ space. Now, let us start from the basic definitions or from the basic diagram about how you can define a consolidation test or an odometric test. Now, as I have said previously that this is a odometric sample that has a height of, let us say, 2 centimeter, and this width is of 6 centimeter. Now, from a 3D view, it looks like a circle of dia 6 centimeter and a height of 2 centimeter. Now, this is placed in a steel ring like this, and a dial gauge is applied. Dial gauge is observed to observe the no change in delta H, where H is the original height of 2 centimeter generally. And what happens is that as the dial gauge reads, different loads are applied on this sample. So, there is a load here, it will be applied to the sample, and as different loads are applied to the sample, let us say it varies from 20 kPa, then 40 kPa, and like that you observe the change delta H by H, and then you plot all these consolidation curves, the square root of time, the CV, then basically the E versus log P. These curves are obtained. Now similarly, just the same case, when basically you are going for recompression, or basically when you are going for a swelling part, what you do is that you remove the load, and you observe that what is the change in the dial gauge. So you get this recompression part, recompression, or you can be termed as unloading part. So this is how in general an odometer behaves. Now see, in the very beginning, when basically you are starting the test, then in that case let us see that what are the stresses in the soil. So when it is first made, then basically the stresses in the soil are actually 0, there is no stress in the soil. Now let us consider 3 directions. So let us say this is sigma 1, just like the previous sign conventions, we will consider sigma 2, sigma 3, means this is 1, this is 2, this is 3. So now, as I have said in the previous problem also, only sigma 1 is the governing factor in case of an odometer modulus, because as you can see, these are steel ring, this is a steel ring. So it bounds the surface like this. So obviously no deformation is allowed along the horizontal direction, no deformation, only vertical direction deformation is allowed, no deformation in these directions. If this is the case, then when you apply the first load, let us say that first load is equivalent to sigma 1 in the horizontal direction, in the vertical direction, sorry, then some changes in the horizontal direction is observed. Though the deformation is 0, means the strain in epsilon 2 and epsilon 3 are supposed to be 0, but actually the stress exists in that direction, because if the strain is, because when you apply a vertical load, then due to the Poisson's ratio of the soil, as you all know from the definition of soil mechanics, it will try to expand in these directions. But since it is prohibited, so basically stresses will develop, which is an internal force. So obviously sigma H, which is equal to sigma 2 is equal to sigma 3, will be equivalent to K naught into sigma 1. Now don't confuse this K naught with the definition of earth pressure at rest. This K naught may be some different K naught, though it is often said that this K naught is actually is equal to 1 minus sin phi dash. But let us for the timing assume that this K naught is just a coefficient that actually is the ratio of the horizontal stress to the vertical effective stress. Okay. So if this is true, then this is equal to K naught into sigma 1. So now from our definition, P, as you know, is sigma 1 plus sigma 3 by 2, while Q is equal to sigma 1 minus sigma 3 by 2. Now this is valid for a 2-dimension case. In 3D, P can be defined as sigma 1 plus sigma 2 plus sigma 3 by 3, while Q is equal to sigma 1 minus sigma 3. Now generally these are termed as the ST tensors. This is also defined by the name of ST, but this is defined as the name of PQ in that case. So since this part is already covered in our syllabus, so we will consider from the basic definition. This part is already covered from this definition of stress path, so we will consider this PQ rather than this PQ. But I will show for a demonstration problem that how this PQ also looks like. So P, now you know, is sigma V plus K naught into sigma V by 2, or it can be written as sigma 1 plus K naught into sigma 1 by 2. So it is equal to sigma 1 into 1 plus K naught by 2. So in the stress space, if this is P, if this is Q, your initial position was 0 0. Now at a particular stress sigma 1, let us say this is my P point. Now what about Q? Q is equal to sigma 1 minus K naught into sigma 1 by 2. So it is equal to sigma 1 into 1 minus K naught by 2. So it is equal to somewhere here. So this is the point, and this line. So, this is the stress path, and the slope of this stress path is obviously q by p, which is equal to 1 minus k naught by 1 plus k naught. So, this is how basically you can define the stress path definition for an odometer. So, for an odometer, the stress path ratio is always in the ratio of 1 minus k naught by 1 plus k naught. Now, for this 3D, for the 3D case of PQ, you can consider this as equivalent to sigma 1 plus 2 into k naught into sigma 1 by 3. So, sigma 1 into 1 plus 2 k naught by 3, and q will be equivalent to sigma 1 into 1 minus k naught. So, in this case, your p should be somewhere here, while your q should be somewhere here. So, it will be at this point, follow a slope of q by p equivalent to 1 plus 2 k naught by 3 to 1 minus k naught. So, 3 into 1 minus k naught by 1 plus 2 k naught. So, that is what is the stress path ratio should be, or basically that is what is the slope of the line is. But for the timing, you should consider only this part, because this is the part that is taught in the syllabus. So, basically this type of questions are very common, that what should be the stress path in case of a consolidation test or an odometer test, and how do you find out from a basic knowledge of the test that how should the stress path be. Now, for the next part, it is asked the stress path of a direct shear test. Now, before we start moving about the direct shear test, let us discuss a bit about the direct shear test and how its stress path should be, just like the consolidation test. So, as you know, in case of a direct shear test, there is a shear box that is again confined in these two directions, and a load is applied from here. This is the normal load, this is the sigma n, or the normal load. Now, this is where the box is supposed to slide. So, obviously the box will slide along this direction, and this is the sigma n. Now, a common question that is often asked in case of a direct shear test is basically, when the box slides, then there should be a area correction. Yes, obviously there should be an area correction, because you see that this is the length that is to be covered, or this is the length that is to be neglected, because this length has already been sheared off by the sample. So, generally what is said is that, since from a 3-dimensional view, if you see the box, it looks somewhat like this. So, this is where the soil is kept, and this is the soil mass that is sheared. So, this part L along, let us say, if this length is, let us say, along x, and if this is along y, then this Ly, as you can see, is changing, while Lx is constant. Now, from the basic, you know that basically the shear box is of a has a dimension of 6 centimeter into 6 centimeter generally, except under only special circumstances where basically you have to consider bigger shear boxes. So, in that case, what you have to do is that a general way to correct the area is that you have to take Lx as it is, and Ly should be minus epsilon, where epsilon is the strain, or basically the strain that you observe, into Ly. That is how your general correction should be. Now, remember that this should be corrected not only for the tau, that means the shear stress, but also at the same time for the normal stress, because you see that the area under the normal stress is also decreasing. So, often in certain books it is ignored that you do not have to calculate for normal stress, but actually you have to calculate both for the shear stress as well as for the normal stress, for the both tau and sigma n, that how your direct shear test is going, that how your area correction is going to come into the factor. So, considering all this, now let us move back to the point where basically we are discussing about the stress paths. So, let us again consider from the basic beginning that how the direct shear test actually gives the definition of the stress paths. So, in the beginning, what you do is that this is how you keep the soil sample as. So, this is the soil sample in between, and the soil and the sample is not subjected to any stresses. Now, what you do is that, so it starts from a point 0 0. Now what you do is that you apply a normal stress sigma n. So in this case, in order to actually compare with the previous definition of consolidation, so we will again consider this as 1, this as 2 and this as 3. Now see, this test is almost equivalent to consolidation test, because here also the confinement is applied on both the sides to a steel body, because you see that this portion is actually steel body. So the soil mass is allowed to move only in the vertical direction, but no displacement along both the horizontal direction. That means again only 1 or epsilon 1 is allowed. Epsilon 1 is not equal to 0, while epsilon 2 and epsilon 3 are both equivalent to 0. So the soil mass is not allowed to move along both the directions. If this is the case, then again from your basic definition of consolidation, stresses will develop, from basic definition of solid mechanics, I am sorry, that stresses will develop both in the second and third direction due to the Poisson's ratio. So again here P will be equivalent to sigma 1 plus sigma 3 by 2, while Q will be equivalent to sigma 1 minus sigma 3 by 2. Now let us consider a Mohr circle and see that how it comes out to. So this is the Mohr circle. So the initial stress, or basically when you apply the initial stress, then immediately along this direction, so sigma 1 is equal to sigma v if you apply, then immediately along sigma 2 and sigma 3 you will see k naught into sigma v, again where k naught is the ratio of the horizontal stress to the vertical effective stress. Remember that all the stresses that we are considering actually here are all effective stresses. So these are all effective stresses. I have just ignored the fact, but these are all actually effective stresses. Because in consolidation, effective stress is the only thing that matters. So obviously these are all effective stresses. So here also k naught into sigma v dash is the effective stress. Right now we are only considered about effective stresses. So sigma 3 dash, one point is here, sigma 1 dash sigma v dash, one point is here. So your Mohr circle looks somewhat like this. So this is k naught into sigma v, while this is sigma v. Now as you apply shear, what happens is that this circle at the end of the shearing, let us consider that at the end of the shearing what happens. So at the end of the shearing, this is what is the condition. Now you see that why I discussed about this area correction, because you see this sigma v or the sigma n that was present has now changed its position, because the area has been changed. So whatever the load was at the beginning, it does not matter, the area now has changed. Similarly the stress has also now changed. So obviously this point has shifted somewhere here. So now let us consider this n as sigma n1 and sigma v1. So this is equivalent to k naught into sigma v1 and this point as sigma v1, thus stress. So this is the final point, and if you join this two line, considering that it is a sand, this is the failure line. So this is different from the, so this is, so basically what now happens is that the stress now has changed in the third direction, sigma in the vertical direction. So since the stress now has changed the vertical direction, so similarly the stress in the horizontal direction has also changed. So k naught into sigma v1 and sigma v1, and now basically when it touches the Mohr circle, when the failure line touches the Mohr circle, then you consider it as the failure point. Now if you do the same thing in case of a direct shear test, then you will see that it will start from somewhere here, then it will go, because here also again E is equal to sigma v dash plus k naught into sigma v dash by 2 is equal to 1 plus k naught by 2 into sigma v dash, and Q similarly is 1 minus k naught by 2 into sigma v dash. So it should again follow a line somewhat here, but remember that this line is going to change accordingly, because this sigma v dash is also going to change. So somewhere this point, this line may go like this. Okay. So in case of odometer and in case of direct shear, the only problem is that the sigma v dash is constantly going to change. So obviously these points, but basically in that case the sigma v dash, whatever you plot it, the sigma v dash there also is going to constantly change, but it is going in linear increment. But here it may or may not go in linear increment, and this k naught may vary depending on the fact that the area is also changing. Okay, so that is why basically this direct shear test is often direct shear test, in case it may not be 1 minus k naught by 1 plus k naught, but generally for the general considerations we will consider it at the time being for 1 minus k naught by 1 plus k naught to be the slope. Another important fact that you have to consider is that in this fact we have totally ignored the effect of consolidation, but in direct shear a consolidated drain test is also possible. So, if you take into consider the effect of consolidation, then in that case it is different from an isotropic compression, because in this case again if you consider the effect of consolidation, then you just apply the load here sigma n, which is equal to sigma v, and you apply the consolidation to occur. Now, obviously you do not know what is the horizontal or what are the horizontal stress. You do not know that, you do not apply any horizontal stress. So, obviously the horizontal stress will be equal to k naught into sigma v dash. So, q in the earlier case, q was said to be sigma 1 minus sigma 3 by 2 for a track shear. In general case q is equal to sigma 1. Now, for a track shear case, what happens is that you know that in case of an isotropic compression, sigma 1 is equal to sigma 2 is equal to sigma 3, that is what I have said in the very beginning. So, obviously in this case what happens is that sigma 1 minus sigma 1 by 2 is equal to 0. So, the line in case of a track shear is actually moves along the P, but in this case what happens is that q is equivalent to sigma 1 minus k naught into sigma 1 by 2. So, it is equivalent to sigma 1 by 2 into 1 minus k naught. So, obviously the line would move somewhere in this direction, because now it has the ratio the sigma 1 dash, and then along the shear it moves along this direction. So, this is for our consolidation line, this is for a shear. So, these are the two definitions that you have to remember, that what happens basically in case of a how basically in case of a direct shear the stress path is going to behave. If it is directly a shearing line, then obviously it should go directly from a shear point from the point 0 0, but if basically you allow a consolidated drain test, for example the CD test in case of a direct shear, then obviously there is a consolidation line, and from that point of the stress, let us consider from this point of the stress, it will move along the shear line. Now, in case of a direct shear, as you have seen that you get a plot of shear stress versus the strain. So, it somewhat looks like this for a particular normal stress. So, this is already known to you. So, I am not discussing all these facts. And one important point regarding the direct shear test is that remember that obviously in direct shear test, since it is confined from all the directions, this I am again telling you that it is confined from all the directions. So, k naught or the effect of k naught should always come into consider in case of a direct shear test. Now, the third type of test where basically the stress path is asked to draw is termed as the standard CD track shear test. Now, this has already been discussed, so I am not going in details, because you already know that this goes in the ratio of 1:3, and if it is a consolidation, then also I told you many times that it will go in this flat portion, and then it will go in the ratio of 1:3. So, in a PQ space where P is equal to sigma 1 plus sigma 3 by 2, this is sigma 1 minus sigma 3 by 2. So, this I am ignoring totally, and the next one is a isotropic CD track shear test, and the fourth one is termed as an isotropic CD track shear test. So, this has already been discussed, because this is the flat portion, and why this is the flat portion, this also I have explained here. So, in case of an isotropic CD track shear test, what happens is that the Q is always 0, that means there is no shear stress generated theoretically, but practically many problems may arise because of the anisotropy in the sample. So, the isotropic CD track shear test basically gives Q equal to 0, there is only value of P, and basically from a standard CD track shear test, the Q is to P ratio always goes in the ratio 1:3, that has already been discussed in the lectures. Now, the last part that basically we are going to cover is basically we have almost discussed, almost every part that we have discussed is basically covers the effect of foundations, the effect of consolidation, the shear strength of soils, and many important aspects like permeability, compaction. And regarding compaction, I also showed one practical problem, that how basically you should assess the degree of compaction when basically a soil sample is given to you. Now, in real life actually what happens is that Now, this is also a demonstrative problem. How basically you can combine all these facts together in one part. So, in real life what happens is that suppose a ground is given to you and depending on that you are asked to perform, or basically you are often asked to find out the strength parameters. GSD, permeability, and one of the most important factors which is termed as the bearing capacity. Often ignoring this term of bearing capacity, people will ask that whether the soil, let us say, will basically adjust or basically can take a load of Q or not. Now, how do you say that whether the soil will take a load of Q or not? The first thing that people does in this case is basically they perform a borehole tests. Now, what do you mean by a borehole test? I have often talked about this. A borehole test means nothing but actually digging the soil profile to a particular depth. Now, once you dig the soil profile to a particular depth, you actually know what type of soil life you are going to encounter. Now, this I have already told in consolidation problem that it is you have to dig almost boreholes depending on the engineer's judgment, or basically from the point of view of the engineer, you have to take different boreholes, means you have to construct different boreholes depending on the test site. So, let us say I have constructed 3 boreholes along this length, and I have observed that the layer of clay actually is here at this point, here at this point, and this point. I said that you join this clay layer and basically, so this is the layer of clay, while this is the layer of sand that you have observed. The water table also you can observe from the borehole, because you know from what point the soil is going to be moist. So, depending on that, let us say the water table is somewhere at this point. Now, apart from all this, once you have done all this, you also know now from the laboratory test, you perform a grain size distribution on this soil, you perform a grain size distribution on this soil. So, obviously, you know what are the grain size distributions now. Now, depending on the grain size distribution, the first thing that you have to do is that the first thing in the report that you have to prepare is that you have to perform a grain size distribution. Then you have to go for a hydrometer analysis. You have to go for a sieve analysis, then you have to go for a hydrometer analysis. Combining these two, you will get the grain size distribution. So, depending on the grain size distribution and according to the IS code classification, now you have to define what is the soil is. So, for that, if it is a fine grained soil, then you have to go for LL, PL, then SL, or the shrinkage limit, or the Atterberg limits. Once you define all these things, then let us say that according to definition, sand is obviously, as we know, is a coarse grain, and let us say that is a well graded sand, while the layer of clay is said to be high plasticity clay. So, obviously HC or CH, the high plasticity clay in the Atterberg chart. Now, once this report has been once you have defined what your soil is at the 2 point, the next thing that you define is basically the water content at the soil, the specific gravity of the soil solids, and from these relations what is the void ratio and the degree of saturation. So, from all this you will get these 4 parameters are very important in real life. So, the void ratio can never be found out actually. Now, this is the trick. The water content you can find out by specifically, because water content you can do it as most people do, is that you can dry it in oven and take out the water content. The specific gravity of soil solids, there is a test for specific gravity of soil solids that I am not going to discuss here, but you can find out. The degree of saturation similarly you cannot find out, neither the void ratio. Now, these two can be found out from, if you can remember, from the basic soil relations gamma D and gamma B. Once you dry the soil, you know what is the volume of the soil, then basically this gamma D can be found out, because gamma D is nothing but the weight of the dry soil by volume of the dry soil. Similarly, gamma B is weight of the bulk soil by volume of the bulk soil. If you remember the relations correctly, then this is G by 1 plus E into gamma W, and this is GS plus AC by 1 plus E into gamma W. So, from both these relations you can derive the E and S. So, you find out the relations of W, G, S, E. Now, you know exactly that what are the different saturation, degree of saturations for this sand at different levels, for this clay at the different levels. Once all this has been prepared, then the next thing that you have to do is basically you have to go for the compaction. So, depending on the compaction, that on which side of the soil, now this is not a necessary case, but suppose you have to ground improve the soil, as I have said that in certain case you have to make improvement in the soil. So, in that case, as I have said, depending on the dry side or the wet side, depending on what your structure is, you have to define then the dry side or the wet side of the compaction. So, depending on whether you want a low permeability soil or a high permeability soil, you will go for a dry side, you will go for a wet side or the dry side of the compaction. Now, the third thing that you have to do is basically about the permeability. So, once you know or once you fix what is your density of the soil is, once you fix what is your gamma B and gamma D is, this two are to be fixed. Now, you know that what is your unit weight of the soil. What is the unit weight? That means what is the gamma B is, and once you know what is the gamma B is, from this from the point of gamma B, you can compact the soil in particular density, and then from there you can find out what is the permeability is. So, that permeability is valid for that particular gamma B. So, that permeability is particularly valid for that gamma B. Now, you can perform a concentrate test, like let us say if you have a layer of sand at the top. So, you are going to perform a concentrate test there, while basically for the layer of clay there, as you know, you have to perform a falling head test. So, then basically the KCl, K clay and K sand has found out. Now, the next part that to move is basically the shear strength and consolidation. Now, these two parameters are going to tell you that whether your soil is going to support the given load or not. So, from the point of shear strength view, from the point of shear strength, what you have to do is that you have to assess that what type of situation is there in the field. So, let us say that you are going to construct an embankment on that soil. This is the layer of sand. Now, the given period for the embankment, now the clay is virgin, or let us say that it has not been subjected to a consolidation before, and this is the water table, and the embankment is to be constructed, or let us say an extra load of 700 kp is to be imparted, let us say within 2 months. The period of construction, during the period of construction, what the constructor said is that basically I am not allowing any drainage. Now, you should know by this time that when you are saying that you are not allowing any drainage, means you are not allowing any consolidation. So, at this point of fact, this entire system now behaves as an undrained system. So, the most suitable test, immediately your judgment should be the most suitable test that you have to perform is a UU test. That means you are not allowing any drainage. So, you are just applying load after load, and you have to see that whether that is able to take that load or not. So, in that case, basically depending on the strain rate, basically you have to perform a UU test. But suppose let us say I have to construct this, I have to construct a building on this soil. And this takes, let us say, 5 years to construct. Now, in this process I am of course allowing a drainage to occur. Now, this is a general judgment that you are of course allowing the drainage to occur. So, if basically you are allowing the drainage to occur, then in that case you have to perform a CD test whether or not the time is sufficient or not, but a UU test will never be able to judge a situation in this case. You have to perform a consolidated drain test in this case in order to get that what are the correct parameters like C dash and phi dash, as you know that in this case the parameter is Cu. So, depending on whether the soil is drained or undrained, you have to judge accordingly that whether you have to take a drain test or an undrained test or not. Depending on whether you are allowing consolidation or not, you have to check that whether the sample is actually allowing drainage or not. So, let us say suppose for example clay takes a very high time to a long time to actually drain. So, obviously when basically the building period, the period of construction is rapid, let us say like 2 months or 3 months, in that case it is obvious that the clay will not drain, and you have to consider the UU case. Now, a general behavior or a general explanation that whether the clay will be draining within 2 months or not is I have showed in an example of consolidation. So, that is where the effect of consolidation actually comes out. So, what you do is that you actually extract a sample of clay, subject it to the same stress conditions. Let us say the embankment load is 700 kPa. So, you subject it to a consolidation of 700 kPa and observe that what is the coefficient of consolidation, let us say from log time method or square root of time method. Now, you will know exactly that I have said like T has to be 99.4% or 99.6% U, then only the total consolidation is supposed to end. So, if this is reached, but basically the coefficient of TV is 2, if this value is reached, then only you say that the consolidation has ended. So, if the consolidation has ended, then only you can say that basically your term means you can perform, you can go for a consolidated drain test. Now, if you see that, let us say that if the construction is happening in the period of 2 months, but however your time takes 2 years to complete, the consolidation takes 2 years to complete, then in that case it is obvious that the situation to be assessed is an undrained, and obviously it is an UU test rather than a CD test. So, this is from where the effect of consolidation will occur. Now let us say that you obtain the parameters C dash and phi dash, and from the consolidation you have obtained that what is the total settlement, because you already know the stress levels, and delta S as you know is Cc by 1 plus E naught. Now, you see E naught you have already found it out from here, into H, you know what is height of clay layer from the borehole test, log sigma naught dash plus delta sigma by sigma naught dash. See, this you will get from consolidation test, this you have already obtained from gamma D or gamma B, this you have already obtained is the from borehole test, and this also from borehole, and this is the height to be placed. So, this is gamma into Z. So, you have obtained every settlement calculations. Now, once you have obtained all these every settlement calculation, you know now that what should be the settlement under that permissible load. If the settlement, since I have considered a virgin clay layer here, so basically I have considered that delta S is actually only available for the virgin consolidation layer, and not I have ignored the pre-consolidation part. Now, one important aspect you have to remember here is that the clay layer may be of varying thickness, that I have also said that in case of varying thickness, how you can use the effect of stress distribution in order to find out the effect of varying thickness. Now, this also, this delta sigma also I have said it to be gamma into Z. Now, you know that depending if it is a footing, that also I have explained, if it is a footing basically how the stress distribution is supposed to be. So, it is going to be P into B plus Z into L plus Z, but Z is this height, this is B, this is L. So, and the load that is coming is P. So, depending on that you have to find out delta sigma. So, all these are to be adjusted accordingly, but the general format should remain the same. So, once you know what is the value of delta sigma, and delta sigma I have found it from log method, you can also find it delta sigma from, as I have said, MV method. Okay. So, any one of them is sufficient. So, once you find out delta S, now as I have said, you know what is your permissible settlement is. So, the first thing, there are two checks that you have to do. The first checks that you have to do is that whether under the clay layer, if the clay layer is uniform, let us say the clay is uniform, then in that case what you have to do is that, what you have to suggest is that delta S, whether it is within S permissible or not. If the clay is non-uniform, then not only you have to check that whether delta S within this permissible or not, but also whether delta S differential is less than delta S differential permissible or not. This is a very important part that you have to check, because you cannot allow detrimental effects to damage the structure. Now, you may ask one thing, that you have to perform a lot of tests in this case. Now, often people what they do is that they will not go for all these tests like this consolidation and all those things. What they will do is that instead they will perform a rapid consolidation problem, and they can find out CV from the relation K by MV into gamma W. So, this is where the permeability actually comes in Q. Rather than performing a test like this, you can directly go from CV by K by MV into gamma W, and you can just assess if basically soil samples are not adequate, or basically you can feel that the time is not adequate, then you can go also for the general formulas that are available, CV by K into MV into gamma W, and from there you can assess out what is the value of, but what are the values of coefficient of consolidation to be. Similarly, you can assess CC from 0.009 into LL minus 10. You all know this formula. So, these formulas are helpful, but a general soil investigation is always required in order to get the parameters correctly. So, once the settlement is checked, now you have to check that whether the load is sufficient or not. Now, this has not been covered, and this is an introduction to the foundation engineering. So, I will just cover a basic formula like the bearing capacity formula C into Nc plus Q into Nq plus B gamma N gamma into half. Now, here Nc and Q N gamma are basically parameters that basically are depending on Nc and Q N gamma are the parameters that depends on phi dash. So, this is where the phi dash comes into problem. This C is the C dash if you consider a consolidated drain test, while basically if you consider an UU test, then what happens is that as you all know phi dash is equivalent to 0. So, this equation comes down to Cu into Nc. So, either using CD or UU, you have to check that whether QU is greater than 700 kPa, which I said is the allowable load or Q load or not, or the load that is to be subjected to the soil or not. So, once all these facts are considered, then only you can say, then only from all these facts or from gathering all the basic soil mechanics definitions, all the soil mechanics problem that you have assessed, you can actually say that whether this QU, whether the soil is actually sufficient against shear strength and settlement or not. So, this is how in real life problems we actually assess a general way of using the permeability, compaction, then consolidation, then shear strength in the field. So, this is where the tutorial session ends. Thank you.